All right, welcome to video lesson 1, getting ready for lesson 3. There are 2 videos to watch before we show up to class on day 3. This one talks about inverses, which is a topic that should be familiar to us from high school. There is no calculus in this lesson. There is no calculus in the next lesson. Let's remember what inverses do. So the basic idea is that if you have some function that looks like this, the inverse of that function undoes what was done. So the inverse of the function, which usually looks something like this, the inverse of that function undoes what was done. You may recall that inverses are reflections of each other over y equals x. Those are mirror images. F and F inverse are mirror images over y equals x. That may be familiar to you. Not all functions have inverses. Functions have inverses if they are 1-to-1. 1-to-1. And f is 1-to-1 if f of x1 is not equal to f of x2 whenever x1 is not equal to x2. And this is the sort of thing that leads to the horizontal line test. The horizontal line test is one of those things that plays in prominently when we talk about inverse functions. The blue function has an inverse that is a function because it passes the horizontal line test. If we were to draw a horizontal line, that's a horizontal line, and we were to move that horizontal line up and down our blue function, that horizontal line never hits that blue function more than once, so the blue function passes the horizontal line test. As a side note, if you had a function like so, this function does not pass the horizontal line test. Why? Because this horizontal line hits the blue function in 3 different points. These are x1, x2, x3, but f of x1 is f of x2 is f of x3, and then this doesn't happen. If you give me 2 different x values, I've got to show you 2 different y values, but here is a scenario where there are 3 different x values all going to the same output. So not all functions have inverses. In this lesson, we concern ourselves with functions that do. For example, find f inverse if f is 2x minus 5. So how does that work? Well, we've already established here that the inverses are reflections over y equals x. How do you reflect over y equals x? You swap x and y. The original function is y equals 2x minus 5. So the inverse is the graph of whatever this is. We normally write that where y is isolated. So to isolate y, we add 5 and divide by 2. And so f inverse is x plus 5 over 2. Of course, it's not always that easy. Find g inverse if g of x is 2x over x minus 3. It's a little bit trickier, same basic idea. The original function is y equals 2x over x minus 3, so the inverse function is whatever this is. But we generally write functions in the y equals form, so this is a problem. It's a problem that can be overcome fairly easily, and we do that by saying, all right, let's cross multiply. At least there are no more fractions. Here a y, there a y, everywhere a y. So let's get the y's all over to one side and the non-y's over to the other side. Why? Because this factors, and then we can divide. So the inverse function is 3x over x minus 2. How do we know that that is in fact the inverse function? Well, we can check if we compose g with g inverse. That has to end up with x. In other words, if we were to take this function and put this in place of x, I will leave it to you to check the details that this function is in fact the identity. You can check those details for yourself. This complex fraction is x everywhere on its domain. Our last lesson was about trig functions, so I would be remiss if I didn't talk about inverse trig functions, because we will talk about those in our calculus course. Inverse trig functions, they're nice and smooth. We as calculus teachers like smooth functions. So the thing about the sine function is that as beautiful as it is, it fails the horizontal line test in about 11 billion places. So to talk about the inverse of the sine function, we have to restrict the domain. We cut things off at pi over 2 and minus pi over 2, and we only look at the sine function in between negative pi over 2 and pi over 2. But if we do that restriction, then negative pi over 2, 1 becomes negative 1, negative pi over 2, and pi over 2, 1 becomes 1 pi over 2, and we flip the function over y equals x, and we get the inverse sine function. So the inverse sine function has a domain of negative 1 to 1 because the range here was negative 1 to 1, and a range of negative pi over 2 to pi over 2 because the domain here was from negative pi over 2 to pi over 2. You can use your graphing technology to take a look at graphs of the inverse cosine function and the inverse tangent function. It would be a nice way to get reacquainted with your graphing calculator. It would be wise for you to be familiar with those graphs and with their domains and their ranges. And we can talk about those when we gather in class. If you are looking, too early. If you are looking for some supplemental practice, if you're looking for some questions to do that would be like things you should know how to do in section 1.4 of the OpenStax textbook, you're looking to do questions 185, 187, 191, 197, 207 and 227. Those are all odd numbered questions, so their answers are in the back of the book hyperlinked, which is nice. You do not have to do those questions. Nobody's going to check that you did those questions, but if you want to ask about them when we gather, you're certainly free to do that. All right, the next video is all about exponential and logarithmic functions. Make sure you click on that also. We'll see you in class.